Okay, so the next thing that we have here is some part called the miscellaneous examples. There are only a few examples over here, and so let's go through them one by one. Example number 11, you want to show that these points, you want to show that basically A, B, C, and D are the vertices of a parallelogram, are the vertices of a parallelogram, ABCD, but it's not a rectangle. But it's not a rectangle. Okay, so basically now we need to know a couple of things about parallelograms and rectangles. So first off, a parallelogram is any geometric shape, or any parallelogram is basically any quadrilateral and you know that the quadrilateral is a polygon. We will talk about this as well. Any quadrilateral in which there are two pairs of parallel opposite sides. So that means that now a quadrilateral is basically a quadrilateral. What that is basically a four-sided pentagon, a four-sided polygon, a four-sided polygon is called a quadrilateral. And hopefully you know what a polygon is. A polygon is a closed geometric actually it's basically I need to write a closed simple geometric shape made up of only straight line segments. So what this means, for example, let's say that for example a closed geometric shape or a closed geometric figure is basically a figure that is, for example, something like this. This geometric shape is closed, is defined as closed. This geometric shape is an open geometric shape. So a polygon first has to be closed, and then it has to be simple, meaning that Now I don't really remember basically what I mean, as opposed to simple, what sort of other geometric shape you might have. But suppose that I have this geometric shape over here. This is a closed geometric shape, but it is not a simple. This is not simple. And the reason why it's not simple is because this side over here is intersecting another side over here. So it's not a simple geometric shape. A simple geometric shape is basically for example, this geometric shape. This is a simple geometric shape in which basically no sides has a point of intersection with any other sides, meaning that the sides don't go over one another. They don't overlap at any point, for example, something like this. So this is called a simple closed geometric shape. Now this is a closed simple geometric shape, and of course you could have a closed geometric shape like this, for example, something like this. But as you can see, this is a curved simple closed geometric shape. It is not a so this geometric shape, you could say that it's made up of a curved, I don't know, line segment or something like that. But the polygon is supposed to be closed. It's supposed to be simple, and it's supposed to be made up of only straight line segments. Now, assuming that these are completely straight line segments, then basically this geometric shape is called a polygon. And then you know that basically when it comes to polygons, of course I didn't mean to talk about geometry here, but now that we are, so let's do it right. Now when it comes to polygons, basically polygons start with basically triangles, meaning that the triangle is the starting point of polygons. So you have a these are basically all polygons. This is a triangle, and a triangle has 1, 2, and 3 sides. So you have 3 sides, 3 angles, and 3 vertices. After the triangle, you have a quadrilateral. For example, this thing over here is called the quadrilateral. Of course, it could be in any other way. It could be drawn really in any other way, meaning that you could draw it, for example, in this way. Of course, this is assuming that this is a completely straight line segment, and these are all straight line segments over here and over here. So this has 1, 2, 3, 4 basically sides. You have 4 vertices, and you have 4 angles. This is because you have 4 sides, it's called a quadrilateral. Then you have a geometric shape which is called a pentagon. So this is 1, 2, 3, 4, 5 sides, and it's called a pentagon. I think it's written like this. I'm not sure about this, but you can look up the spelling of pentagon if you or let me do it actually over here. So a pentagon. So a pentagon is actually written with an A. So this is called a pentagon. So 5 sides and 5 angles and 5 vertices. Next, what you have after pentagon, for example, you could have a hexagon. A hexagon has basically hexagon. It has 6 sides. So you have 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. This is called the hexagon. Then you have after hexagon, you have something which has 8 sides. I'm sorry, 1, 2, 3, heptagon. Then there is the heptagon, 7 sides. Then there is the heptagon. Heptagons, okay. Then there is the heptagon which has 7 sides. Then there is the octagon. No, acht is 8 in German. We can look it up actually. So you can polygon with 8 sides. In geometry, an octagon. So it's called an octagon. So if you have basically 8 sides, then that's called an octagon. I already forgot that. Octagon. And then there is something called the nonagon. I suppose, for 9 sides. And then there is something called, for 10 sides, there is also a name. Let me see if the nonagon is right. Nonagon. And then, let me see. Nonagon, and then polygon with 10 sides would be decagon. D-E-C-A. So that is called a decagon. And so on and so forth. And of course these hexagons you can have, for example, when it comes to for example, let's say when it comes to a polygon, for example, to a pentagon, for example. When it comes to a pentagon, it has 5 sides, and so it's supposed to have 1, 2, 3, 4. It is supposed to have 1, 2, 3, 4, and 5, something like this, right? So if, for example, if you draw it in such a way that all the angles are well, it's I mean, there is this whole world of the relationship between the angles and everything in these in these polygons. For example, you can have you can draw this in such a way that, for example, your angles are in a certain way. For example, something like this, and then, I don't know, something like this, for example, and then connect these points together. And if you basically draw it in a certain way, it's going to be called a regular. It's going to be called a regular pentagon, which I don't really know what, I mean, the definition for that we can look up. For example, a regular Pentagon is as you can see, I think all the side lengths are equal. A polygon is regular when all angles are equal and all the sides are equal. Otherwise, it's called irregular. This is a regular pentagon, a 5-sided polygon. So all the sides are equal and all the angles are also equal. So that's basically some information about these polygons and so on and so forth. Now, one case of these polygons is called the quadrilateral. The quadrilateral is basically the type of polygon where you have 4 sides. It's a 4-sided polygon. Now, if you have a 4-sided polygon or a quadrilateral in which basically there are 2 pairs of parallel opposite sides, for example, something like this. This is called, so if this is parallel to this one and if this side is parallel to this side, so this, you have 1, 2, 3, 4 sides. You have 4 sides, so it's a quadrilateral. It's a quadrilateral. And also, basically, you have 2 pairs of opposite parallel sides. 2 pairs of opposite parallel sides. Parallel sides. That is called a parallelogram. And basically with the same definition, of course, a rectangle is also a case of a parallelogram, or basically a square. Or a square is also a case of a parallelogram, and there are some other geometric shapes that are also special cases of a parallelogram. Now, over here in this example, the term parallelogram has been used a little bit loosely, and so basically you have these 4 vertices over here, these 4 points in space. And you want to show that these points are the vertices of a parallelogram, and by that, what is meant is just strictly this geometric shape, but it's not a rectangle. Okay, and by rectangle, what is meant is basically this geometric shape. Okay, so that's basically what the question is. Now, there is, wants to restart itself. Postpone. Okay, so now there are basically some properties of these. There are some properties of a parallelogram and a rectangle that we need to use here in order to basically show that basically this geometric shape is basically a parallelogram but not a rectangle. And what that is that if you show that basically it's a fact that in a parallelogram and but again by a parallelogram what I mean is basically this geometric shape. And by a rectangle, what I mean is basically this geometric shape. Okay. So in a parallelogram, opposite sides are equal. The opposite sides are equal. Moreover, it is not a rectangle. Now in a parallelogram, and also in a parallelogram, the diagonals are not equal. But as you know, in a rectangle, of course, as you know, in a rectangle, the diagonals are actually equal. And of course, you know that in a rectangle, the opposite sides are of course equal. So if you can show that basically the opposite sides in a quadrilateral are equal, it could be a parallelogram, it could be a rectangle, it could be a square, or any other possible basically geometric shape. Now if you show that the diagonals are not equal, then that means that then your geometric shape is definitely a parallelogram, and again by a parallelogram what I mean is this geometric shape. Now this basically, if you can show these two, basically if you can show these two things over here, then you can basically show that ABCD is a parallelogram but not a rectangle. Okay, so this way you can solve the problem. Now there is one more thing over here that you can also use alternatively. Now there is a property that might be useful to you in some situations, and that is in a parallelogram. In a parallelogram, basically the diagonals bisect each other. The diagonals bisect each other. So if you basically show this in the case of any quadrilateral, that means that that's a parallelogram, and of course that is the case also in a rectangle. Also that is the case, because as you can see over here, this diagonal bisects this diagonal, and this diagonal bisects the other one. So, but basically to show that a geometric shape is a parallelogram, it's enough to show that, for example, the diagonals bisect each other. That you can do, or you can show that the opposite sides are equal. That is also basically enough to show that a geometric shape is a parallelogram, for example. So we are not going to use this, and that only because that's not been used in the book as well. We are going to simply use the formulas that we know in order to show these two, and then that shows that the geometric shape is a parallelogram but not a rectangle. So now, in order to show that the opposite sides are equal, what you can do first, let's see what the points are here. The points that we have are basically we have A, which is 1, 2, 3. We have B over here, which is -1, -2, and -1. We have C. Which is 2, 3, 2, and we have D, which is basically 4, 7, 6. So now if you plot these points in a 3D coordinate system, this is the x-axis, this is the y-axis, and this is the z-axis. So you have 1, 2, 3. So 2 would be over here, comma 3 would be basically 1, 2, and 3 over here. This would be point A. And then point B would be -1, -2, -2, and -1 would be some point over here. This would be point B. This would be point B. And then point C would be basically 2, 3, 2. So 2, 1, 2, and 3. And 2 would be 1 and 2. This point over here. This is point C. This is getting a little bit crowded. This is A. And this is B over here. And then we have the point D, which is 4, 1, 2, 3, and 4. 7, 1, 2, 3, 4, 5, 6, and 7. And +6. 1, 2, 3, 4, 5, and 6 over here. This is point D. And if I connect these points together, I will get this geometric shape. So now we know basically that what we can do is that we need to show that the opposite sides are equal. That means that we need to show that AD is equal to BC and AB is equal to CD and AB is equal to CD. So all we need to do is use the and also to show that it's not a rectangle, we need to show that basically AC is not equal to BD, and also show that AC is not equal to BD. So that's basically that. So now I'm going to erase all of these things. And the formula that we are going to use in order to find the distances we are looking for is basically the distance formula for the 3D plane or the 3D system. It's basically if you want to, for example, if you want to find that the distance AD or any other distance for that matter, that's the square root of x2 minus x1 whole squared plus y2 minus y1 whole squared plus z2 minus z1 whole squared. And so AD is equal to, for example, AD taking the points A and D would be 4 minus 1 whole squared plus y2 minus y1, 7 minus 2 whole squared plus 6 minus 3 whole squared. And that is equal to the square root of 3 squared is equal to 9, 5 squared is equal to 25, and 6 minus 3 squared is equal to 9. 18 plus 25 is equal to 25, 18, that's 13, 1, that is 13, 1, and 43, that's the square root of 43. And I don't think 43 can be written as anything really. So AD is equal to the square root of 43. Is equal to the square root of 43. Now, the next thing that we have is, I wish I hadn't erased that part. Okay. And now go over here. Okay, so now the next part that we have is, for example, BC. BC is the square root of, so these 2 points, so 2 plus 1 whole squared plus 3 plus 2 whole squared plus 2 plus 1 whole squared, and that is equal to the square root of 9 plus 25 plus 9, which is equal to 18 plus 25 is again 43, the square root of 43. So that means that BC is equal to the square root of 43. Now, the next thing that we have is, for example, this distance over here, AB. AB is basically these 2 points over here, so -1 whole squared plus -2 minus 2 whole squared plus -1 minus 3 whole squared, which is equal to the square root of -2 squared is equal to 4, -4 squared is equal to 16, -4 squared is equal to 16, 32, 36, which is equal to 6. So AB is equal to 6. Next, this distance over here, CD, is equal to the square root of 4 minus 2 whole squared plus 7 minus 3 whole squared plus 6 minus 2 whole squared, which is equal to the square root of 2 squared is equal to 4, 4 squared is equal to 16, 4 squared is equal to 16, 32, 36 is equal to 6. So CD is equal to 6. I don't know what it was, but something, oops. The other computer got restarted. It's Windows update. Suppose. It doesn't matter. Okay, so now we have all of these distances. Now the only thing that we need here is again AC and BD. So AC is equal to the square root of these 2 points, 2 minus 1 whole squared plus 3 minus 2 whole squared plus 2 minus 3 whole squared, and that is equal to the square root of 1 squared, which is equal to 1. 1 squared is equal to 1, and -1 squared is equal to 1, which is equal to the square root of 3. So AC is equal to the square root of 3. And basically BD, these 2 points, 4 plus the square root of 4 plus 1 whole squared, 7 plus 2 whole squared, 6 plus 1 whole squared, which is equal to the square root of 25 plus 81 plus 7 squared is equal to 49, and that is equal to 49 plus 81 plus 25, 15, 1, 10, 15, 155, the square root of 155, which is, well, I don't know what 155 is, so 155 divided by 5 is equal to 3 times 5 is equal to 15, and 1 times 5 is equal to 5, 31, 155, 5 times 31, and 31 is not divisible by anything, so just write it as basically BD is equal to the square root of 155. Now, what that means is that now you can show that of course you can see that basically you can see that AD is equal to BC is equal to the square root of 43, and AB is equal to CD, and AB is equal to CD is equal to 6. Therefore, ABCD is a parallelogram, and these are basically the opposite sides. The opposite sides are equal in length. And then AC is not equal to BD. AC is not equal to BD, and what that means is that the diagonals are not equal in length. Which means that basically meaning that ABCD is not a rectangle. That's basically, that is what we wanted to show over here. Is not a rectangle. Okay. So basically, again, I repeat this. What you need to because this will be repeated in other exercises all throughout these books. These are the famous things about these geometric shapes that usually appear in these exercises. So in the case of a parallelogram, the opposite sides are equal in length. And also the diagonals bisect one another. The diagonals once bisect one another. Now in the case of a rectangle, the diagonals are equal in length. Which means that if you show that basically the diagonals are not equal in length, that means that it's not a rectangle. Okay. So that's basically the whole story here. And we have 2 more examples here. We will solve them as well, and then we have a couple of exercises here as well. 6 more exercises to go. Okay, so the next question that we have is find the equation of the set of points P. Find the equation of the set of points P such that its distances such that its distances from the points A 3, 4, -5 and B -2, 1, 4 are equal. Okay, so basically to find the equation of the set of points such that the distances of these points from the points A and B are equal. So if you imagine that, for example, the coordinates of the point P are X, Y, and Z, then the distance AP, for example, would be the square root of x2 minus x1 whole squared minus y2 minus y1 whole squared plus, actually these are all positive, plus z2 minus z1 whole squared. So AP is equal to the square root of, basically you can write, for example, x minus 3 whole squared plus y minus 4 whole squared plus z plus 5 whole squared. That is the distance AP. Now by the same logic, the distance BP is equal to x plus 2 whole squared plus y minus 1 whole squared plus z minus 4 whole squared, the square root of that. Now if the distance between P and both of these points are equal, I can write AP is equal to BP. That means that these two are equal, meaning that the square root of, and of course if that is the case, I can write AP squared is equal to BP squared, because I want to get rid of these square root functions. So that means that I can write x minus 3 whole squared plus y minus 4 whole squared plus z plus 5 whole squared is equal to x plus 2 whole squared plus y minus 1 whole squared plus z minus 4 whole squared. And if I simplify this, this is a 4 actually. This is a 4 over here. And this is also a 4. So that is x squared plus 9 minus 6x plus y squared plus 16 minus 8x plus z squared plus 25 plus 10x plus 10z is equal to x squared plus 4 plus 4x plus y squared plus 1 minus 2y plus z squared plus 16 minus 8z. And so you can simplify x squared with x squared, y squared with y squared, z squared with z squared, and then, for example, 16 with 16, and so I can write negative 6x, negative, that is supposed to be y actually, negative 8y plus 10z plus 10z, and then plus 9 plus 9, and then we have plus 25 is equal to, or take these to the other side, negative 4x plus 2y and plus 8 times z, and then 4 plus 1 is equal to 5, so minus 5 is equal to 0. Now, negative 6x minus 4x is equal to negative 10x. Negative 8y plus 2y is equal to negative 6y. And 10z plus 8z is equal to 18z. 9 plus 25 is equal to 34. 34 minus 5 is equal to 29. Plus 29. 20 plus 29 is equal to 0. And we cannot simplify this, so the equation of the line is 10x minus 6y minus 8. Okay, so we can rewrite this as 10x plus 6y minus 18z minus 29 is equal to 0. And that is the equation of those points. Now, if you want to see what that actually means, we can actually go over here and plot these points and see what we get. So I'm going to delete and reload this page, and I have basically 2 points over here, which are 3, 4, negative 5, and I have another point over here which is negative 2, comma 1, comma 4, and I have another line which is not really sure if that's that might actually be a plane, basically 10x plus 6y minus 18z minus 29 is equal to 0. That is a plane. So, and the question is find the equation of all the set of points. We're not talking about lines, we're talking about a set of points. And as you can see, so here we have as you can see, the points are basically one of the points is up here, one of the points is down here, and you can see that the plane, and the equation of the plane is this thing that we found. The plane is basically at an angle to the xy plane. It is equidistant from both of these points, which is pretty interesting. Okay, so the next question that we have is question number 13. The centroid of a triangle ABC is at the point 1, 1, 1. Centroid of triangle ABC is at 1, 1, 1. If the coordinates of A and B are, if the coordinates of A are 3, negative 5, and positive 7, and the coordinates of B are negative 1, 7, negative 6, find the coordinates of the point C. What is the coordinates of the point C? So your triangle is basically you know that the centroid of a triangle, if you have a triangle over here, the midpoint of this side, if you connect this vertex to the midpoint of this side, this is called the median. And also the midpoint of this side connected over here, this is also a median. And then this will also be median. The point where the three medians meet is called the centroid. It's called the centroid, which is basically the point of intersection. The point of intersection of the three medians. And one more thing that we also talked about in the previous videos is that the centroid basically I think it was 1 to 2. The centroid basically what it does is that it divides the median, or any median, divides any median of the triangle in the ratio I think 1 to 2. 1 to 2. That means that the centroid is always 2/3 of the way from any vertex to the base of the triangle. I suppose that's the case. Now we can of course check this. Centroid of triangle, and if you go to Math Warehouse, for example, there is this in the ratio 2 to 1, or 1 to 2 basically. So if you start from this point, for example, the ratio would be, for example, 2 to 1, of course. Or you can take it as 1 to 2, but then you have to go the other way around. So the ratio 2 to 1. Meaning that the centroid starting from any vertex is always going along. The median is always 2/3 of the way along the way to the base of the triangle. That's what that means. So what that means is that your triangle is basically at this point. Your triangle is at this point X, Y, and Z. And, well, 3, negative 5, 7 would be 1, 2, 3. Negative 5 would be 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5, and 7 would be over here. 1, 2, 3, 4, 5, 6, and 7. This is the point A, for example. Now point B is negative 1, 7. So 1, 2, 3, 4, 5, 6, and 7. This is the point on the this is the point on the XY plane, and negative 6. So you have 1, 2, 3, 4, 5, and 6. This is the point, and then this is the other point. So this point is point B, this point is point A, and then the centroid is at 1, 1, 1, meaning that at 1, 1, so over here 1, 1, 1 is basically at this point over here. This point would be the centroid, for example, that I call it G, for example. That I call it G. What that means is that well, anyway, these two sides have to be connected, but it seems to be a rather weird triangle. But of course we are looking at this in a 3D, meaning that this point is back there and this point is over here. So what we need to do is that suppose that your triangle is basically something like this, and suppose that this is A and this is B, and somewhere over here is your centroid G. Then the midpoint of B and C C would be over here. This goes through this line. This is the midpoint of B and C. This is the midpoint of B and C, of BC. And this, call it for example D, and basically G divides AD in ratio 2 to 1. So so now what we need to find out is this point over here. So the way that we can find it is basically find, so since we have the coordinates of this point and the coordinates of this point, we can find this point using the section formula. And then using the midpoint formula, we will be able to find the coordinates of this point. So step number 1, what we can do is that we can find basically coordinates of D using section formula. And step number 2, basically find point C, coordinates of C using midpoint formula. So then what I'm going to do is basically come down here, and using the section formula, I'm going to find the coordinates of D. So since G is dividing this line segment internally in the ratio 2 to 1, then the coordinates of G are equal to basically m times x2 plus n times x1 over m plus n, and m times y2 plus n times y1 over m plus n, and m times z2 plus n times z1 over m plus n. And So the coordinates of G are 1, 1, 1. Your M and N are 2 and 1. M to N is equal to 2 to 1. So over here I can write basically 2 times some number plus 1 times some number, so I don't really need to write that 1. And over here I need to write 2 plus 1 is equal to 3. Again over here 2 times some number plus some other number is equal to 3 over 3. And over here again 2 times some number plus some other number over 3. Now over here I need to take this point as point 1 and this point as point 2. Okay, so that means that if I take the coordinates of D as basically x, y, and z, what that gives me is that then I want to take D as point number 2. So over here I have basically x2 minus x2 over here and x1 over here. So I have to write my x over here, I have to write my y over here, and I have to write my z over here, because these are the coordinates of this point. And x1, x2, x3 are the coordinates of this point, point A. And point A are, the coordinates of point A are basically 3, -5, and 7. 3, -5, and 7. So x, 3, -5, and 7. So then we can calculate these, meaning that we can find the coordinates of x, y, and z, which are the coordinates of the point D. So basically I can write 1, 1, 1 is equal to basically 2x plus 3 over 3 and 2y minus 5 over 3 and 2z plus 7 over 3, which means that 2x plus 3 over 3 is equal to 1, meaning that 2x plus 3 is equal to 3 and 2x is equal to 0. That means that x is equal to 0. Now 2y minus 5 over 3 is equal to 1, which means that 2y minus 5 is equal to 3, which means that 2y is equal to 8. That means that y is equal to 4. And over here I have 2z plus 7. 2z plus 7 over 3 is equal to 1, which means that 2z plus 7 is equal to 3, which means that 2z is equal to -4, which means that z is equal to -2. So the coordinates of the point D are 0, 4, -2. 0, 4, -2. Now what I can do over here now is basically do step number 2, which is, of course, it seems to me that the solution that we have, had in the book was much simpler, very much simpler, but let's continue with this. Now, using the midpoint formula, you know that D is the midpoint of B and C. So the coordinates of the point B are -1, 7, -6. And I take the coordinates of this point C as x, y, z. So the coordinates of the midpoint of these 2 points would be D, which would be basically x1 plus x2 divided by 2, y1 plus y2 divided by 2, and z1 plus z2 divided by 2. And the coordinates of this point D are 0, 4, negative 2 is equal to basically negative 1 plus x divided by 2, 7 plus y divided by 2, and negative 6 plus z divided by 2. Which means that 0 is equal to negative 1 plus x, which means that x is equal to positive 1. X is equal to positive 1. And x minus 1 is equal to 0. X is equal to 1. 7 plus y over 2 is equal to 4. 7 plus y is equal to 8. So y is equal to 8 minus 7, which is equal to 1. And negative 6 plus z over 2 is equal to negative 2. So negative 6 plus z is equal to negative 4. Z is equal to negative 4 plus 6. Z is equal to 2. So the coordinates of this point would be then 1, 1, 2. 1, 1, and 2. The answer is correct, but the solution that we had in the book was much simpler. And let me read the solution here. It says that let the coordinates of C be x and the coordinates of the centroid be y. Then oh, okay. Well, anyway, I don't really understand the solution over there, but this way we can actually find the coordinates of that point as well. Over here, what they have done is that they have written the coordinates of C. The coordinates of C they have taken as x, y, z, and the coordinates of the centroid as 1, 1, 1. Okay. X plus 3 minus 1 I think somehow they have used the section formula, but it's not obvious how. But anyway, that doesn't really matter. Okay, so the next thing that we have here is a couple of exercises, which is basically the miscellaneous exercises on chapter 12, which we will do in the next video. See you in the next video.